Hello, everyone. So I think I'm the only lecturer this year who will be talking about hardware, and I want to start out by especially for those not familiar with hardware development, give an idea for what this world looks like and why it's interesting. And let me just start out by doing that by drawing a picture. I'm going to switch back and forth between Emacs and Blackboard. So probably most of you have seen diagrams of circuits. Let's just draw one concrete one here. I'm going to draw a bunch of little boxes which stand for gates that take some inputs and then produce some outputs. And it won't be too important for this level of abstraction what the function is that transforms the inputs into the outputs. Let's say, so this top row here, these are all the inputs. Think of these as maybe wires coming in from the outside world or something. And then we start computing some derived values. And finally, let's say this guy at the bottom is the final answer. And I'll put this in here. So we have these physical elements that have input signals flowing in and very quickly transform them into output signals flowing out. Maybe each of these lines is a 1-bit wire, or maybe it's something more interesting than that. The cool thing about diagrams like this, as we think to what we're used to doing in software, where people work really hard, for instance, to get good performance by introducing parallelism into programs. The cool thing about this diagram, I'm just going to sort of do a topological sort kind of thing, indicate these boxes up at the top are the inputs, and then this next group here, I'll say these constitute round one, because as soon as the inputs are determined, we can evaluate both of these, and they naturally run in parallel. So with hardware circuits, the really cool thing is that parallelism is the default, and to some extent you have to make an effort to not get parallelism. So that has good consequences for performance. And then happens there's just this one gate that runs next on round 3. And then let's say, sorry, I meant 2. Round 2 and round 3. So in general, we're just sort of following the topological sort kind of order. And conceptually, every one of these layers in the topological sort runs simultaneously. And then we can trace, for instance, let me pick out this path here, which we could call a critical path, which is the longest path from one of the inputs to one of the outputs. And that path basically determines how long this circuit takes to execute. So we typically think in terms of concepts like clock cycles on digital hardware, like the processors in our laptops, where we imagine everything runs instantly. But of course, in the physical realization of running one of these circuits one step all the way through, there is some propagation delay of signals coming down from, in this kind of diagram, from the top toward the bottom. It does take physical time to compute answers and then send the answers out over wires. And so really the running time of a circuit like this is proportional in some sense to the critical path. And I'm using the cartoon version of this stuff here. I know there are several people in the audience who know the low-level details of this better than I do. But this is the basic idea. We get parallelism for free, and the time for one of these wire propagations is so much faster than the time for one instruction running on a laptop, for instance. So there are a lot of opportunities to get performance in styles that are very different from what we're used to in software. And then just to give a sense for how this kind of picture fits into the story of how, say, a processor is developed, here's the workflow that we typically have as I understand it. Again, I'm straying a little bit away from my own knowledge here because I only know some of the steps in this kind of diagram. Typically, people write scripts that are going to build their hardware designs for them because working directly at a low level is too unpleasant. So these scripts are generally using what I'll call metaprogramming, or programs that produce programs. And you run one of those and you kind of get a flat version of a design. And this can be compiled into something called RTL, which stands for Register Transfer Language. And at this point, think of this as gates and the links between them, but no geometry. We don't know exactly where the different elements of our circuit are placed in space. We just know what the elements are and how they're connected to each other. And then there's a whole suite of tools that would eventually produce an implementation in silicon at the end. And typically, especially from this part, everything is proprietary, and even people using the tools don't know all the details of how they work. So the Coq framework I'll be presenting is basically at these levels, the Kami framework. We have some ongoing work to extend the system, including proofs to RTL. But at the moment, we're reasoning about programs that produce descriptions of circuits. And by the way, this circuit is what we call a combinational circuit. It's just it's like a functional program, computing a pure expression or a pure function of the inputs. And in the later lectures, we'll see state and some sort of feedback within circuits that persists across time. So that's all in the Kami framework. And I'm going to cover three basic subjects across these three lectures. Today, what I'll be focusing on is how we embed languages in Coq. And at some level, I'll just happen to use the example of a language of combinational circuits, but we'll see some general tricks to get languages with nice looking syntax and flexible semantics embedded inside of Coq so we can write programs and prove theorems about them. Then tomorrow, I want to focus on modular proofs, how to take a program in your embedded language and divide it into modules or libraries and prove things about each part individually and then snap those results together. And finally, when we have all these preliminaries in place, the last day, I want to focus on how we verify computer processors. And we'll look at some of the first baby steps of optimization in getting a processor that works sort of like the ones in our laptops and desktops work, and showing that it implements a much simpler specification that is independent of those optimizations. All right, so haven't gotten into too much technical detail yet, but are there any questions at this point? Yeah?
In the flat process, does Kami unroll everything in the script?
Can you repeat the question?
The question is, in this arrow, does Kami unroll everything? And I'd like to ask for clarification about two small points. What is unroll and what is everything?
Unroll means if the script has a loop.
Yeah.
Do you have to?
All right. There are no loops left in this code. Okay. So if we're only talking about loops and recursion, the answer is yes. They're all gone by the end of the run better programs part.
So the compile time will be essentially the runtime of the script.
Compile time of the overall system is identified with the runtime of the script. Yeah. Any other questions? Yes.
Is there a silicon developed, which was developed via Kami?
Not quite, but with a closely related system, there are some very widely used deployments, and I guess I should mention this. Kami is Kami is based on a hardware description language called BlueSpec, which does have commercial uses and uses in research projects that have actually fabricated chips. That hasn't yet happened with a design that was proved with Kami, as far as I know, but I'm expecting in the next few years there will be some first examples of that. And I'll say more about BlueSpec tomorrow. Today we'll be sticking to some pretty basic stateless circuits that don't need the interesting features of BlueSpec. But Kami is inspired by an existing language called BlueSpec. Question, yeah?
So if the script has state, will there be like loops and like as flip-flops in by the like flat level, or does that happen like later on?
The scripts do not typically have state, at least in our realization of that idea, they don't. Probably they do in industry. I hear that Perl scripts are popular for this sort of thing, and you can imagine that doesn't make every day a happy one. Any other questions? All right, so let's just start getting into the right mindset here. And I want to work out an example on the board, and then we will look at some calc code that makes it all more executable and provable. So general functionality I want to implement is let's build an infinite family of adders. In general, what I'm going to assume is, let's say, so I'm drawing a little box with an 8 inside. This is going to stand for an 8-bit number. And let's say I have a bunch of these. I have n 8-bit digits that together are interpreted in the usual way as one big 8n bit number. And I have another of these too. And I want to add them together and get, well, we might need one more digit at least. Actually, just one more bit would be enough. I'm going to make this simpler and give us a whole additional 8-bit digit. And so we're adding two numbers. Assume we have pres primitives available to us, an adder for 8-bit numbers, and I want to build up to an adder for 8n-bit numbers. And again, there's an extra digit down here because these both might be all 1 bits, and then the result would overflow the original size and need to go a little bit larger. And just for simplicity, I'm using only 8-bit digits here, though I could have said just one bit down there. All right, so if we're trying to write down a general recipe for building an adder of this form, assuming we have adders for, I think I'm actually going to assume we have 9-bit adders. That'll be the most useful. How would we write down a recipe for using 9-bit adders to build this more general addition with digits? I'll start us out by suggesting we're going to write this recursively. And that means there'll be a base case and an inductive case. The base case is pretty easy here. What if we have 0 digits and we're adding another set of 0 digits? Actually, this is not going to be quite trivial. A nice helper function for this code is going to keep track of carry flags. So I'll use a more general version where we're adding two big numbers and 1 bit that is a carry flag to give us 8 bits of output. And the way I'll represent this is just taking that 1 carry bit and adding some extra zeros onto it so it becomes an 8-bit number. And now this is an implementation of the adder where the digit lists are empty. We just propagate the carry flag into the output. Does that make sense? Any questions here? Yes?
I'm a bit confused. The 8, is that a duplication or is it the number of bits in that register? So do you have 8 registers of n bits or do you have n registers of 8?
When I write the numbers inside boxes, they're the bit widths of those registers.
So that means n registers of 8-bit and you do 8-bit addition.
Yeah.
Then I don't understand on why do you have an n plus 1? Shouldn't it be n boxes with 9 in it? Or?
I'm down one of these rows. I'm interpreting this as a multi-digit representation of a large number. We're not just doing n separate additions down the columns. Yeah. All right, so let's look at then the inductive case of this construction. So I'll give myself n of these 8-bit numbers and then one additional one on top. And likewise over here. And we have 1-bit carry flag. Any ideas how we would start defining the general case for how we're going to interpret both of these columns as multi-digit representations of numbers, And let's say the top here is the least significant digit in each case, and we want to get the sum of both columns, also with the carry bit added in. I'm just going to sort of draw circuits and connect boxes to each other, and hopefully it'll make sense as a correct implementation of this. And so assume we have some basic bitwise operators and as well as 9-bit addition built in, and everything else we have to describe. Yeah?
Add the lower order bits, and the carry out of that goes into the one carry in of the inductive phase.
Okay, yeah, so you said we're going to add these and basically add these three in this arc at the top. I'm going to be a little more pedantic than that, just so that this maps directly into the code that I'll write. First, I'm going to 0 extend the lowest order digit of one input to 9 bits. I'm saving time and not labeling these arrows, but think of this as we used a 0 extend operation. This is a 0 extending gate or something. And I'm going to 0 extend the lowest order digit of the other one. And now I'm going to add these together. I'm going to take my general adder and add all these together. I'll label this with a plus. This is using our built-in plus. So we have these two 9-bit numbers and this 1-bit number, which actually, to be completely pedantic, I will also 0 extend the 1-bit number. So this one needs 8 zeros added onto it, whereas these two just need 1 0 added on. And then use my built-in adder, which is able to handle this case. It might actually be 2 adders chained together. And then the easy part is I'm going to extract the lowest order 8 bits of the result of this addition, and I'm going to copy those into the final answer, which will have an 8 part and an 8 times n plus 1 part. So just copy that into that position. And then you mentioned something interesting about an inductive case. So let's assume we have a recursive instance where n has gone down by 1. And it needs 2 digit sequences and a carry flag. Well, let's give it the remainder of the digits that we didn't already use as its first 2 inputs, and then we can extract the highest order bit of this addition and plug that in as the third input of the recursive instance. And then the output of the recursive instance goes into determining the highest, all the bits of the output except for the lowest digit worth. Any questions here? Next step is to see it in calc code, which, depending on your brain wiring, might help or make it worse. Let's say I'm defining a function here called add, and it has 3 arguments. The first one is this digit sequence, the second one is this digit sequence, and the third one is this carry flag. So we're going to have a calc function that does that momentarily. Any questions before I jump into that calc code? All right, so now we are starting to see some actual code that uses parts of the Kami library. To begin with, I'm just going to be relying on the definition of a type of bit vectors, which is a dependent type indexed by the number of bits in a vector. So I can define capital B as type synonym for a byte, which is a word with the index filled in as 8 bits. And then one of these multi-byte things that I was drawing is going to be a vector of bytes. And the multi-byte itself takes as an index the length. How many digits are in this multi-byte representation? And we have this handy function that converts a multi-digit representation into a single natural number, where an empty representation stands for 0. And then when we cons a byte onto the front of another representation, we can shift the meaning of the rest of it by multiplying by 256 and then add in the nat version of the 1 byte on front. And then this recursive definition is what we were just drawing. It takes in a carry and 2 multi-byte things and outputs a multi-byte of length 1 more. So when the length is 0, we take the carry, we combine it with 7 0 bits. That was the 0 extend I was talking about. and then that becomes the single